Well, good afternoon from Paris, everybody, and welcome to the Energy Technology Perspectives 2017 webinar. My name is Elina Levina, and I'm the project manager of the Energy Technology Perspective 2017, and I will be moderating today's presentations. As an introduction, I'll say a couple of words about the ETP project and how we'll proceed in this webinar. As many of you know, the Energy Technology Perspectives ETP series is the IEA's comprehensive publication focusing on technologies and policies that contribute to the energy sector decarbonization while enabling energy security and economic development. Since 2006, the IEA has been providing strategic guidance on energy technology and policy through this publication, keeping stakeholders informed about technological trends, advances, and opportunities. As integration and the role of bioenergy in low-carbon scenarios. The Global Outlook chapter will be presented today and also on July 10th. Today we have 6 presentations. Each presentation will last about 15 minutes, and at the end of the webinar there will be time for questions. Before we start, we would like to express our gratitude to around 200 contributors and reviewers. The report benefited from data expertise and valuable feedback provided by many colleagues outside and inside of the IEA. I would like to mention in particular And now I would like to pass the microphone to our director, Kamal Ben-Nasur, who will provide us with a setting presentation and give us. Kamal, you have the floor.
Thank you very much, Elina. Good morning, good afternoon, and good evening, everyone, and welcome to this first webinar of ETP 2017. The publication was launched at the Clean Energy Ministerial that was held earlier this month in Beijing. The executive summary is available for a download at the IEA website, and the book is also available for purchase on the IEA website. As ETP came in 2006, and at that time we had essentially 3 scenarios. One that was called the blue scenario, which was became the 2-degree scenario. This year we have a significant enhancement to the model, and we have introduced a new scenario which we call beyond 2-degree scenario, or well below 2-degree scenario. And also in terms of time scope, we will be looking at 2060. And this is extremely important because we start seeing the the potential of going carbon neutral within the simulation period. So moving to the next slide. Where are we today? First one is there are signs that the global energy markets are changing, and the pace of change is extremely fast. Just to give you some points, the first one is that renewables have supplied half of the global electricity demand growth in 2016. Nuclear has also reached, in terms of the increase, its highest level since 1993. The second one, in terms of the way we use energy, is that the global energy intensity has improved by 2.1% in 2016, and there have also been very significant efforts around the world in terms of reforming fossil fuel subsidies. The third one is on technology progress and its impact on the demand for energy services. So electric vehicles, for instance, are now common offerings across the major auto manufacturers, with decreased
Amal, we don't hear you very well. We're losing you. Yeah.
Yeah, so call again. Try again.
Could you try again, because we lost you after the electric car sentence. No.
I need to call again.
I think yes. Il faut envoyer le... Mais il faut continuer, poursuivre. Ouais.
So what should But we can hear him.
We can't hear.
No, we can hear. We hear some noise, but not your voice. I think all the participants probably hear the same.
Yeah.
Maybe you could call us on the mobile phone in addition to being connected through computer. Maybe that would work. There should be a number provided, I guess, when you register. Kamal, we're calling you on the phone, and we will put the phone to the microphone here in the room, so everybody then could hear you from the phone. So could you please respond to the call from Olivier right now, and then we'll connect you here. So we have Kamal Benacer on the phone, and we'll try again. So can you try, Kamal?
Yeah, okay.
Feedback.
Do you want me to do the presentation?
No, you continue and back to.
No, it doesn't work.
And we continue with the rest.
Do you want me to just do it?
Yeah.
Okay. Okay, everyone, we apologise for the technical difficulty. We had Kamal dialing in from off-site, but clearly there's a problem with the phone connection. My name's Samantha McCulloch. I work in the CCS unit here at the IEA, and I was the lead author of the Global Outlook chapter. If you're happy to bear with me, I will proceed through Kamal's slides now before we move to the Global Outlook chapter. So as Kamal was saying, we've seen a very rapid transformation of the energy sector in recent times, particularly considering an historical context. Kamal was just finishing up talking about electric car sales, but we've also obviously recognised that the energy sector remains key to sustainable economic growth. There is still 1.2 billion people who lack access to electricity, 2.7 billion people who lack access to clean cooking, and of course the energy sector remains the largest source of greenhouse gas emissions and a major source of air pollution, and these are concerns that are increasingly driving policy and investment decisions today. In terms of how the transformation of the energy sector might proceed, there's no single story, and fast-paced technological progress and changing energy business models will ultimately determine what the transformation looks like. So the energy landscape has been shifting. In the first decade of this century, we saw quite an amazing increase in energy demand from around 10,000 million tonnes of oil equivalent to almost 13,000. And this was primarily fueled by coal, which provided almost 50% of that growth. However, since 2010, energy demand has increased much more slowly, less than a third of the growth of what we saw in the earlier part of the century. And this was met almost equally by oil, gas and renewables at close to a third each, with a slight role for coal at around 10%. The global energy intensity of GDP declined by around 12% between 2010 and 2016, or looking at it another way, it's improved by around 2.1% per year. So some of the trends that we've seen in terms of the global energy system have shown, according to IEA analysis, that we've now seen global CO2 emissions flat for 3 consecutive years. This has largely been due to developments in the US and China particularly. In the US, the shale gas revolution has seen a switch from coal-fired generation or decline in reliance on coal-fired generation and increased use of gas. And in China, we saw emissions decline by around 1% in China, even though economic growth was sitting at more than 6%. And that was really a story of increased penetration of renewables in the energy system and some developments in relation to nuclear, where we had 5 new nuclear plants come online. In the buildings and industry sector in China, we've also seen a switch from coal to gas, and that's largely being driven by air pollution concerns. So it's too soon to say if emissions have peaked, but this decoupling of economic growth and emissions will certainly need to be accelerated if climate targets are to be achieved. So as Kamal introduced earlier, in this year's ETP we look at 3 very different scenarios for the future energy system. Our baseline scenario is the reference technology scenario, and this scenario includes current and announced policy measures, and that does include things like the commitments that were made in nationally determined contributions that were pledged in the lead up to the Paris negotiations in 2015. It is not a scenario that would be consistent with meeting long-term climate ambitions, but it would see future temperature increases of around 2.7 degrees by 2100. So while it's not as an aggressive a climate scenario as our other scenarios, it actually does represent a significant departure from a business as usual approach where, you know, if there were no meaningful emissions reductions measures. We also look at a 2-degree scenario, which, as the name would suggest, would aim to limit future temperature increases to 2 degrees by 2100. There is a considerable gap between the RTS and the 2DS of around 760 gigatons of CO2 that would need to be abated cumulatively over this period. And then our analysis looks at what the most optimised, cost-effective approach to achieving these emissions reductions across the energy sector would be. And we find that the mix of technologies needed is as follows. There's significant contribution from energy efficiency at around 40%. Renewables also do much of the heavy lifting at 35%. Fuel switching 5%, nuclear at 6%, and carbon capture and storage technologies in both industry and power provide around 14% of those emissions reductions. Now, as Kamel also mentioned, for the first time this year, we looked at what would happen if we pushed this portfolio of technologies to its maximum practical limits and how far we could move beyond a 2-degree pathway. And the outcome of that was our beyond 2-degree scenario. Now, these additional... Hello? Oh, I think we have Kamel again.
Okay, apologies. Thanks, Sam, for the jumping in. Can you hear me?
Yes.
Okay. So, as Samantha said, we are now considering another scenario, which is the B2DS, the beyond 2 degree, and this is not an attempt to put a definition on what the Paris Agreement has called a well below 2 degree scenario. It is a scenario that is between 2 and 1.5 degrees, and this scenario corresponds to a carbon budget of about 700 gigatons compared to about 1,000 gigatons for the 2 degree that Samantha just described. So the difference between those two is about 300 gigatons. This scenario takes us to about a 1.75 degree with a 50% chance. So the difference between the 2 degree and the B2DS is also expressed in terms of wedges, with the constituents of the wedges being efficiency 34%, CCS 32%, renewable, and fuel switching representing the major other ones. I just want to highlight here that this is not the total in terms of contribution, but this is just the incremental compared to the 2 degrees. The graph on the right side shows how much in terms of abatement the different wedges would contribute, with a solid line corresponding to getting to the 2 degree and the hashed one corresponding to B2DS. So as an example, efficiency would contribute in a B2DS to remove a total of 400 gigatons. The second biggest wedge would be renewables with about 300 gigatons, and this is followed by CCS with about 190 gigatons. So what we see, for instance, is that nuclear between the 2DS and the B2DS does not increase significantly because most of the potential would have been exploited in the 2DS. Going to the next slide. One part that is highlighted in the publication Tracking Clean Energy Progress is on the status of clean technologies today. And we have a traffic light indicator with red being technologies that are not on track. And actually, the progress rate is significantly below what we would expect for 2° and even more for a B2DS. And among those technologies are the biofuels for transportation, buildings, CCS, and more efficient coal-fired power. Today, we still have a number of subcritical units that are being commissioned. Moving now to technologies that have made progress, but there is a significant need for accelerated improvement. We have nuclear. We have technologies on the end-use sector that, like lighting, which has moved to about 15% for LEDs in terms of total residential sales, and we expect that to grow to 30% in 2016. Energy-intensive industrial processes is also an area that needs focus, and this will be further looked at in future publications of ETP. And then transport, fuel economy of LDVs is also an area that requires significant focus. Moving now to technologies that have made progress and that would put us on track with a 2° scenario. Electric vehicles, as we will see in a couple of slides. Energy storage in terms of the speed of deployment, and then solar PV and onshore wind, which have made remarkable progress, as mentioned in the first slide. Moving to the next slide, let's just look at the evolution of the electric mobility. In terms of fleet, we see there a breakdown of the number of electric vehicles in the road. And the very good news is that after the 1 million mark that was passed in 2015, we have passed now the 2 million mark in 2016. And we have a year-on-year sales growth of 40% in 2016 after 70% in 2015. So that decline in sales growth is concerning. That means that we still need quite a significant focus on policy support. If we look at now in
Kamel, we've lost you again.
We've lost you again, so we'll probably now switch to Samantha again. Sorry. I really apologize to the audience for these technical difficulties.
Okay, so as Kamel was saying, in terms of the technologies that are on track, wind and solar are certainly performing well on the back of strong policy support and some impressive cost reductions that we've seen in those technologies. I might just skip through this in the interest of time. Of the technologies that are not on track, carbon capture and storage is a key one, given its role in industry and in power generation. If we look at the portfolio of projects, we currently have around 17 large-scale CCS projects operating around the world and across a number of different applications, including coal-fired power generation, bioenergy. There's a bioethanol plant that commenced operation this year in the US, oil sands processing, natural gas processing. So there's a suite of projects that are currently operating and also coming online, but the scale of this falls well short of what would be needed in a 2-degree pathway So even if all projects were to go ahead, we'd be capturing less than 70 million tonnes a year of CO2 in 2025, from around 30 million tonnes today, and we would need to see that increasing tenfold to be consistent with a 2-degree target. But we'll have a deep dive into CCS later in the webinar. It's clear from our analysis in terms of the portfolio of technologies that need to be developed and where we are in tracking with key technologies that there is a need to significantly boost technology innovation and clean energy research, development and deployment. Despite the growing need, we've seen that global R&D spending has effectively plateaued at around $26 billion annually, and this is mainly coming from governments and state-owned enterprises. Now, to try to put this in some context, the top 3 IT companies, and that is Amazon, Google and Intel, spend more on their R&D than the entire global clean energy sector. However, the establishment of Mission Innovation, which was an initiative that was announced during COP21 in Paris, provides a really important opportunity not only to boost the quantum of investment in clean energy R&D, but also in terms of encouraging greater collaboration for research and development. Under that initiative, 22 member governments have agreed to double their global R&D or their research and development spending, which could provide around another $30 billion in R&D support by 2021. In conclusion, we've seen that early signs do point to changes in the energy transformation, but this would need to be significantly accelerated to be consistent with climate goals. Achieving carbon neutrality by 2060 would require an unprecedented technology policies and investments from where we are today, and continued technology innovation remains critical to delivering these pathways. Now, we might just quickly move to the overview of the Global Outlook chapter. So in this chapter, we provide I guess an overview of the modelling outcomes and an introduction to the rest of the book. As Kamel has already covered, that despite the recent promising trends that we've seen, the current efforts are really not consistent with long-term climate ambitions. However, a clear outcome is that we need a portfolio of clean energy technologies in terms of an optimised, cost-effective pathway to 2 degrees or below. I note that in all our scenarios, we look at technologies that are currently commercially available or that are at a stage where they could become commercially available within the scenario period. But as I just outlined, continued technology innovation is really critical, no matter which pathway that we're looking at, in order to improve technology performance, to reduce costs and to pull through some of those more nascent technologies. I note the outcome of our aggressive B2DS scenario was that we could achieve net zero CO2 emissions from the global energy sector by 2060. This is technically feasible based on the portfolio of technologies that we examined, but it would require a fundamental and immediate shift in the current level of global action. So this slide just provides a bit of a perspective in terms of the cumulative energy sector budgets for the 2DS and the B2DS. Moving from the reference technologies, so scenario, which is roughly where we're tracking today, to a 2-degree scenario would require around 760 gigatons of CO2 emissions to be abated over the scenario period. To put this in some kind of context, that's around 22 years worth of current annual emissions from the energy sector. And for the B2DS, the carbon budget is reduced by around 2/3, and as you can see, there's a much faster trajectory towards a carbon neutral energy system. Now, the shift to a 2DS would require a fundamental change to the global energy mix. Fossil fuels provide around 81% of the primary energy mix today, but this this would fall to around 35% by 2060 in the 2DS. And that represents an absolute decline of around 230 exajoules or 50% from today's level. And coal use experiences the largest decline, falling by around 72% over the scenario period in the 2DS, and that's in absolute terms compared to today. The growth in primary energy demand would also need to be limited in the 2DS. In the RTS, you can see it increases by almost 50% over the scenario period, but in the 2DS, this is restricted to 17%, including due to rapid and aggressive implementation of energy efficiency measures. Now, the transformation of the global energy system at this scale requires efforts across all supply and demand sectors. The rapid decarbonisation of the power sector is a key strategy for achieving the 2DS. Renewable energy technologies, CCS and nuclear deliver significant emissions reductions to support this decarbonisation. However, the electrification of end-use sectors also plays a critical role in the 2DS. The share of electricity in the final energy demand of the key end-use sectors, so that's transport, industry and buildings particularly, the final energy demand doubles from around 18% to 35% in 2060. The shift is even greater in the B2DS, underscoring the importance of electrification for these sectors in achieving deep emissions reductions. But this also means that the power sector has the dual task and the dual challenge of absorbing this increasing electricity demand while also rapidly decarbonising. Early action on energy efficiency is a critically important strategy for the end-use sectors also. We saw earlier that energy efficiency provided around 40% of the cumulative emissions reductions needed in the 2DS. It's particularly important, you can see there, in the building sector, where emissions need to be reduced by around 85% relative to the reference technology scenario. In the industry sector, energy efficiency accounts for around 2/3 of the sector's cumulative emissions reductions in the 2DS. CCS also plays an important role in the industrial sector, particularly in the shift to deeper emissions reductions needed in the B2DS pathway. And we'll have a more detailed look at the industry sector later in the webinar. So in terms of understanding the challenge of shifting beyond the 2DS, it's quite useful to look at the remaining emissions in the 2DS scenario. So you can see in the purple wedge there, the power sector is virtually decarbonised by 2060 in the 2DS, and the largest sources of emissions are the industry sector at almost 60% and the transport sector at around 36%. So these are emissions that would need to be tackled in terms of moving to a net zero pathway for the energy sector. So in our B2DS, you can see there's a much faster decarbonisation of the power sector. By 2050, we see the average emissions intensity of power approaching zero, and thereafter it actually becomes a source of negative emissions, and that's through the combination of bioenergy with CCS. In the industry sector, you can see there has been significant emissions reductions, and CCS has also played a key role in terms of delivering those deeper emissions reductions in industry, and more aggressive policy measures in the transport sector also see the transport sector emissions significantly reduced. However, even with these very aggressive measures, there's still around 4 gigatons of emissions from those sectors that are either too complex or too cost prohibitive to abate directly, and that's where those negative emissions from CCS with bioenergy are used to directly offset those remaining emissions in those end-use sectors. Now, the fuel mix in the power sector looks vastly different in these scenarios to what it does today, as one would expect. There's significantly reduced reliance on coal and gas-fired power generation compared with today. In the 2DS, there's virtually no unabated coal, and half of all generation from gas-fired plants comes from plants equipped with CCS. In the B2DS, there's almost no room at all for unabated fossil fuels, and also greater reliance on bioenergy with CCS to provide those negative emissions I spoke of earlier. I'm going to skip 2 slides, which you can look at in terms of the building sector and also the role of electrification of light and heavy duty vehicles in the transport sector. Let me just touch on the availability of sustainable bioenergy. So bioenergy plays a key role in all of the scenarios. Even today, it's the largest source of renewable energy globally and accounts for around 11% of total primary energy supply. In the RTS, the contribution of bioenergy grows by 45%. That's despite a decline in traditional use of biomass. And in the more ambitious scenarios, the availability of sustainable biomass is likely to be constrained, largely due to social and environmental issues such as land use impacts. And so we've therefore capped its availability at around 145 exajoules in both the 2DS and the B2DS. However, how this bioenergy is used between these 2 scenarios changes, and most notably, a greater proportion of the bioenergy needs to be coupled with CCS to maximise those climate benefits and to provide negative emissions. So there's obviously quite a significant gap between where we're currently tracking in a 2DS pathway. That's a gap that obviously increases with more ambitious targets and ambitions for below 2 degrees. A significantly strengthened and accelerated policy framework will be required, irrespective of whether the world is aiming for a 2 degree or below 2 degree target. And while we have specific policy recommendations in each of the chapters in the ETP, some of the overarching priorities that were identified included greater support for technology innovation, as I spoke about earlier, greater RD&D investments, a better alignment of long-term climate ambitions and near-term policy actions, which could support more efficient investment decisions in the near term and a smoother transition, and improved integration of policy measures across the energy system will be needed, including to account for the growing electrification, for example, of end-use sectors, and to support more optimal use of limited resources such as bioenergy. So with that, we might move on from the Outlook chapter and start the deeper dive into some of the sector-specific chapters.
Yeah, thank you very much, Samantha, especially for also stepping in and delivering 2 presentations in one go. Apologies again for the technical difficulties. And without further ado, and to save the time that we lost a little bit at the beginning, we'll dive now deeper into this electricity sector. And we have 3 analysts who led the chapter, and one of them, Uwe Remmer, our energy analyst and modeler in the ETP team, will present one part of the electricity transformation chapter, and then there'll be a second part on the infrastructure that will be presented by Luis Munuera. So Uwe, you have the floor.
Thank you very much for the introduction, and also hello to everyone outside listening. So yeah, I would like to talk about what's happening in our power sector analysis in our scenarios in ETP this year, and I would like to start looking at the electricity demand. At the global level, electricity has been the fastest growing final energy source, increasing at an average annual rate of 3.4% per year over the last 4 decades, and overtaking natural gas in 2001 to become the second largest final energy source after oil globally. As a result, the share of electricity in global final energy consumption almost doubled from 10% in 1974 to around 18% in 2014. In all 3 scenarios, global electricity demand will continue its historic growth path. In the 2DS, electricity overtakes oil and becomes the largest final energy carrier by 2050. In the below 2 degree scenario, even by 2040, underlying the strong electrification trends in this scenario. Efficiency improvements and electrification have to go hand in hand, with efficiency gains reducing or even offsetting rising electricity demand in other parts. Thus, energy efficiency also helps to reduce the impacts of electrification on the generation infrastructure. Increased electrification, in particular the transport sector, brings also global final electricity demand in the below 2 degree scenario almost back to the levels in the reference technology scenario. Overall, the share of electricity in the global final energy mix more than doubles from 80% today to around 40% by 2060 in the beyond 2 degree scenario. The highest electricity share is actually observed in the building sector, so our homes, where we have today a share of around 30%, and that's doubling to 61% in the beyond 2 degree scenario. So now looking how this electricity is generated in our scenarios. In the beyond 2 degree scenario, the power sector is completely decarbonized by 2050 with its CO2 intensity reaching 0. This is 10 years earlier than actually in the 2 degree scenario. Already before 2050, once the carbon intensity is sufficiently reduced, electricity can also support CO2 reductions in the end-use sectors through electrification, for example, heat pumps in the building sector industry, or also electric vehicles in the transport sector. In the years after 2050, the CO2 intensity even becomes negative in the B2DS. That's due to the deployment of BECCS, reaching globally a capacity of around 300 gigawatts in 2060, and the development of bioenergy with CCS or BECCS in the power sector results in negative emissions of almost 2 gigatons in 2060. It helps to offset remaining emissions in the power sector itself. We talk about fossil CCS, the remaining emissions from coal CCS, but in particular BECCS in the power sector is needed to offset emissions in transport, particularly industry, to overall reach the target of net zero emissions of the energy system in 2060 in this scenario. Reaching the beyond 2DS requires some drastic changes compared to past trends in the generation mix. So coal-fired power generation without CCS has to be phased out by 2035. That's 5 years earlier than in the 2DS, and also requires early retirement of coal capacity in the order of around 1,300 gigawatts globally. CCS retrofits of around 170 gigawatts can to some extent alleviate the need for early retirements of coal in this scenarios, but the retrofit potential is also limited at some point because coal with CCS also becomes too carbon intensive at current assumed capture rate in the below 2 degrees scenario. I will come back to that, explain it a bit more later in my presentation. Then if you look at nuclear electricity generation is almost tripling globally by 2060 compared to today, and renewables, including BECCS, account for almost 80% of the electricity generation in the B2DS in 2060. If we compare the 2DS with the below 2 degree, we see some changes, particular low generation from gas without CCS, and even less coal with CCS in the B2DS compared to B2DS, and this declining generation is replaced by renewables and BECCS in the B2DS compared to the 2DS. So the basic changes that we see between these two scenarios. As Samantha mentioned earlier, the power sector is key for the decarbonization of the global energy system. In terms of cumulative emissions, the power sector provides around 40% of the CO2 reductions needed to move from the RTS to the below 2 degree scenario, and more than half of these reductions are actually coming from renewables, excluding bioenergy with CCS here, while CCS including BECCS, so bioenergy and fossil CCS provide 40% of the CO2 reductions, and nuclear accounts for around 12%. Also, the absolute difference in the emission profiles between the B2DS and the 2DS, which is shown here as the dashed or dotted line, seems or may appear small. Reaching net negative emissions levels represent significant change compared to the 2DS and the below 2 degree. As said before, BECCS capacity in the order of around 300 gigawatts is globally needed, and that would correspond to a bioenergy consumption on the primary energy level of around 24 exajoules in 2060, or 1/6 of the global total primary bioenergy demand in the below 2 degree scenario. This clearly puts challenges in terms of sustainable bioenergy supply, because bioenergy is not only needed in the power sector but also in other energy sectors. And then we also have to think about the competition of land for energy, for other needs, particularly the need for land for food production. So even if the difference in the power sector is rather small in terms of the total emission, it's quite a step change that's occurring, moving from the 2 degree to the beyond 2 degree scenario. That becomes also apparent when looking at the marginal abatement cost that we see in the power sector. in these scenarios. So in the 2-degree scenario, we have a marginal abatement cost of around $240 per ton of CO2. In the below 2-degree scenario, this marginal abatement cost CO2 price more than doubles to around $570 per ton of CO2. The challenge of the beyond 2 degrees scenario becomes also apparent when looking at the investment needs in the power sector. So achieving the decarbonization levels set out in the B2DS requires investments globally in generation, but also transmission distribution of around 61 trillion US dollars between 2017 and 2060, or on average 1.5 trillion US dollars per year. Just to put that number into perspective, 1.4 trillion US dollars per year is roughly twice the amount that has been spent last year, 2015, globally in the power sector, where the investments have been estimated to be around 700 billion US dollar. Comparing the investment needs to the 2DS, the B2DS requires 23 trillion US dollars more than, requires 6 trillion US dollars more than the 2DS, and compared to the RTS, the increase is even 23 trillion US dollars. So that overall, the additional investment needs in the B2DS actually, compared to the additional investment needs of reaching the 2 degree, actually 40% higher. So that again stresses really that we see a step change in terms of the efforts needed in the power sector to go to net negative emissions. On a regional level, around 60% of the cumulative investments in the 2DS and the B2DS are needed in the non-OECD countries. That's actually a similar share that we also observed in historically, for example, in 2015. It may be interesting to note that together 3 countries, namely China, India, and the United States, account for almost half the global investment needs of the power sector in those scenarios. That's really, again, a concentration, because particularly if you look at India, where we expect increase in electricity demand due to rising income levels. That's really where we see then also the investment needs to be happening. In the following, I want to look at a closer look at 3 main technology options to decarbonize the power sector, namely renewables, CCS, and nuclear. So starting with the renewables in the power sector, they actually become the dominant generation option in the 2DS and also the below 2 degree, with the share of renewables in the global electricity mix tripling from 23% in 2014 to 72% by 2060. That excludes BECCS. And with small emission reduction targets, renewable share increases to 74% in the below 2 degree scenario. Of this, solar, PV, and hydro each account for about 9,000 terawatt hours of electricity production in 2060, and that compares to a global generation level of around 53,000 terawatt hours. Wind power even produces 10,500 terawatt hours in 2060 in our B2DS. And just to put that number into perspective, around 10,000 terawatt hour, that's the current generation of the 2 largest electricity generation producers, the United States and China combined. If you look at the deployment of low carbon technologies, particular solar PV stands out. There we see an increase of solar PV capacity globally to 4,400 gigawatts in 2050, and beyond that, by 2060, we see an increase to around 6,700 gigawatts globally in the B2DS. And the growth in solar PV capacity is fortunately facilitated by the fact that large parts of the increased demand of electricity fortunately occur in regions with relative good solar potential, such, for example, India, Africa, the Middle East, or parts of the United States. Renewables are responsible for more than half of the cumulative CO2 reductions in the power sector in the B2DS, again relative to the RTS, but also require almost 80% of the cumulative investment needs in power generation in the B2DS. In the B2DS, the global average annual share of renewables increases from 4% in 2014 to 80% in 2030, and doubles then again to 37% by 2060. That clearly stresses the need for increased flexibility of the electricity system, and my colleague Luis Muller will talk later about that in more detail, how that can be achieved. As already said before, CCS is currently playing virtually no role in power generation, with only 3 large-scale power plants with CCS being in operation, representing a combined capacity of around 1.3 gigawatts and the potential to capture around 4.2 megatons per year. If you look at the 2DS and B2DS, the rapid uptake of CCS in each region globally, installed capacity of almost 1,000 gigawatts by 2060. Overall, CCS and B2DS provides around 20% of cumulative emission reductions relative to the RTS in the power sector. And while electricity generation from gas and biomass-fired CCS power plants actually increasing in the B2DS, we see a decline of coal-fired power generation with CCS after 2045, and that can be explained by the remaining emissions of coal-fired power plants with CCS. So typically in our scenarios we assumed capture rates of around 85 to 90% of the CO2 being captured, but it still also means that, for example, if we have a post-combustion power plant with capture rate of 85%, it's still 125 grams per kilowatt hour are still emitted. So which then compares to what I've shown before, CO2 intensities getting zero, even negative in the 2DS and B2DS. So clearly, if coal with CCS should be able to play a role after 2050 in these ambitious climate scenarios, one really has to think about to investigate higher capture rates. So that's also one of the recommendations for RD&D. What would be needed in terms of technology? What would be the cost implications for higher capture rates going beyond 90 or 95% to really reduce the remaining emissions of coal with CCS? The last technology I want to look at is nuclear. Today, nuclear is providing low carbon electricity already at scale, with a share of 11% in the electricity generation mix and installed capacity of around 418 gigawatts in 2060. Nuclear electricity generation is among the low carbon power technologies, second only to hydropower. So again, hydropower is the largest one, followed then by nuclear. And in terms of generation, nuclear electricity generation in 2016 has been 3 times generation of solar and wind combined. However, one also has to be clear that nuclear faces various challenges, not only public concerns about safe operation, and questions of long-term disposal of spent nuclear fuel, but also economic challenges and very capital-intensive technology. In the B2DS, nuclear power benefits from the stringent carbon constraint, providing around 12% of the cumulative CO2 reduction in the power sector, and its generation share increasing to 15% by 2060. Interesting aspect maybe to note is that if we look at the regional capacity deployment, we see really that the growth for nuclear has to happen in non-OECD countries, particularly China, which in 2016 our B2DS accounts for 28% of the global installed capacity. Having that said, I just want to conclude with a few recommendations for the power sector in the 2DS. So the first one is something I guess ETP has been saying for many years, that technology support has to be adapted to a technology's maturity. So that's not a new message, but what I would like to stress here is that with more stringent decarbonization goals, it becomes more and more important to look not only at individual technologies in installation, but also at the linkages and dependencies between technologies and sectors to identify cost-effective opportunities for the transition of the energy system. A case in point is here, for example, electrification of heat and transportation. As also mentioned already by Samantha, there's also a need for strong carbon policies, for example, like CO2 prices, but carbon prices alone are likely not able to deliver the investment certainty needed for these investments in capital-intensive power technologies in these ambitious climate scenarios. So additional policy support instruments are needed, in particular in the transition of the system that we face today, which is often in many countries still very much dominated by fossil fuels, to a low carbon or even zero carbon power system that we see in the 2DS, or even in a net negative power sector that we see in a below 2 degree scenario. Renewables are becoming the backbone or dominant source of electricity generation in our 2 scenarios, so in the 2DS, but also in particular then in the below 2 degree scenario. facing challenges, particularly if we talk about the integration of variable renewables. Again, my colleague Luis Monero will talk about it in a minute. And as I also mentioned, coal-fired power generation without CCS has to be phased out by around 2040 or 2045 in our scenarios in both 2DS and B2DS to minimize stranded assets. At least new coal-fired power plants should be CCS ready, and we should also focus research and R&D, as mentioned before, on increasing the capture rates of coal-fired power plants with CCS, so that then they could also have a perspective in these very ambitious climate scenarios like the B2DS. And BECCS will play a critical role in reaching the B2DS, it's not necessarily needed for the power sector on its own, but in particular to provide net negative emissions to the remaining part of the energy system, particularly where it's more difficult to decarbonize, like industry and transport, particularly there, given the challenge of sustainable bioenergy supply. One recommendation that we have here is that we should, for example, look at improving the efficiency of smaller plants, smaller BECCS plants to be able to provide sufficient resources for bioenergy with CCS in various regions, countries. That's all I wanted to say. Thank you very much.
Well, thank you very much, Uwe. I would also like to acknowledge Raymond Malishek, another author of this chapter, who is in the authors but wasn't part of the presenters, and also maybe Eric Mazanet, who I haven't acknowledged, another author of the Global Outlook chapter and overall analyst of this report. And I would like to pass to Luis, who will present infrastructure needs in order to fulfill these challenges of advanced and enhanced electrification and decarbonization of the electricity sector that Uwe has just described. And I would also like to mention, if you have any questions, please send them to us while speakers present so we can see them before we start the question and answer session at the end. Thank you very much, and Luis, you have the floor.
Thank you, Elena. So what we wanted to do with this presentation is to give you a little bit of a taste. We will have a second webinar on July 10th, where we will focus in more detail on the system integration issues, more focus on the demand side as well, where a lot of these deeper changes are happening in terms of infrastructure. But we wanted to give you a bit of a taste of, at a very high level, what is the deep transformation of generation that my colleague Uwe has just described in detail. What does that entail in terms of the infrastructure needs and the supportive infrastructure? And as I mentioned, some of the very, very deep changes that need to occur to facilitate these deployments. What you see here is the annual, a very similar figure that my colleague Uwe has shown already. The annual investment needs separated in generation and in transmission and distribution. Those that happened last year in 2016, those that need to happen in terms of average annual investments between today and 2050 in the B2DS, and then in the last decade. And what we see here is, first of all, huge increases as has already been described. We also fundamentally see a very different geographical mix of investments. So in some countries where a lot of these technologies that I will describe in terms of smartness and new approaches to building out the infrastructure need to happen in areas where traditionally they have not been doing so much. You will notice in particular Middle East and Africa, we will have an energy and development special from the IEA's World Energy Outlook coming out in the fall. Where we will look into a lot of detail on what happens with the electricity infrastructure, transmission and distribution in Africa. But in particular, what I want to highlight here is that the investments really need to accelerate, especially in the final decade. And I wanted to zoom into transmission and distribution, which can often tends to be forgotten when one talks about transforming the electricity sector. So what we see is a bit of the context setting for the different areas that we looked at in the ATP, in this year's ATP. What we see is that a lot of the transformation needs to occur, particularly in electricity distribution networks. There's a a lot of distributed capacity that's being connected at medium, low voltage levels in power grids. A lot of the new technologies that are coming in, particularly in terms of electrification of the demand side, electrifying heat, electrifying cooling, also the growth in electric vehicles that has already been shown. All of these require some form of adaptations locally. At the same time, we also have growth in storage and rapidly reducing costs, which are also changing where some of the flexibility occurs, at what level of networks, with a lot of potential for it occurring in distribution networks. And finally, a more flexible demand side. At the moment, as most of us will know, most of the demand is passive. Electricity flows from centralized plants unidirectionally towards the demand side. What we see in the B2DS is that there's a lot of flexibility that needs to occur on the demand side in industry, in businesses, and in homes as well. In particular, what we see is that even from the very short term, if one wants to reach the levels of the deployment that we see in 2016 in the B2DS, the investment distribution grid needs to accelerate very quickly. What you see here, one has to break from historic trends almost immediately. This is a particularly challenging sector for investment. It's not very fast-moving infrastructure. It's very, very long-lived. And even within the energy sector, is not the most innovative. That needs to happen, change needs to happen very quickly. At the same time, the whole of the infrastructure becomes more distributed. Here you have also from the chapter, you have how the costs of battery storage have been evolving over time. We see an 80% cost reduction over the past 7 years for batteries, which is a very similar in terms of learning to what we saw for solar PV in the early 2010s. And in particular, we think for every doubling of storage volume, or how much storage is in the system, around 20% cost reduction can be expected. But what we see here is that a lot of this learning, a lot of this deployment will actually not happen in the power sector. It will be dwarfed by the amount of batteries that are produced in electric vehicles in particular, which will also dwarf the current production of batteries for consumer electronics. So that means that there will be very, very dramatic cost reductions that we expect. Because of that, in the chapter we look at what needs to happen in terms of technological needs to break through some of the lower bottom thresholds that we see right now for the current technology of batteries, what kind of innovations need to occur. And again, here you see a very dramatic growth, particularly in B2DS for all kinds of batteries, but in particular for EVs. This also means distributed and moving capacity for storage that needs particular infrastructure to be integrated. So in terms of how does one make some of these new demands like EVs, a lot of electrification for heat, for cooling, industry as well, a lot of electrification potential there. How does one make it part of the solution and not so much part of the problem? We looked at some solutions there. In this case, we have chosen electric vehicles. What you see here is if one charges electric vehicles according to the current usage of a typical car, there is an expected growth in terms of peak capacity needs that is not particularly sustainable. However, with some of the smart charging solutions that we explore there, one can smoothen demand a lot more, integrate EVs both in terms of the system, total system cost, the generation and so on, but also within distribution networks. So we have an estimate for both the 2DS and the B2DS for the demand shifting potential for electric vehicles, but also for a range of other demand side sources of flexibility. and what we see there is that there's a rapid scale up again as before, particularly in the latter periods to meet the B2DS goals. There are, however, very important uncertainties for diffusion, scale up of a lot of demand response, less so for EVs, but in particular how consumers will take some of this flexibilizing of demand, what kind of business models could emerge, and so on. And in this sense, maybe worth noting that we are working right now at DIA on a report on digitalization. Will also come out in the fall, and we will explore in much more detail a lot of these connectivity issues relating to the digitalization of the demand side. Third pillar of this enabling infrastructure for the reductions in the B2DS is storage. So moving into more detail into storage, a lot of the trends right now are being captured by battery storage. Here we group everything together. All types of storage are not from hydro. Most of the growth that you see there is actually from batteries, or other forms of storage of non-pump hydro storage are pretty small. This is true that there has been a very, very fast growth, and there are a lot of policy-driven initiatives around the world, mandates, new markets being created where storage can compete. But when one looks at actually the global installed capacity of storage, it's still a very small portion, and will probably continue to be in the short term a small portion of the global installed storage, dwarfed by pumped hydropower storage. And it's an area that's still growing. There's around 20 gigawatts of pumped hydro plants coming online in the next 5 years. So there is still, while we, again, as Samantha showed in the introduction for tracking clean energy technologies, storage was shown as green. This is a very promising area in terms of enabling infrastructure, but it starts from a very low base, and the growth is very uncertain. So I think this is more or less this overview of the enabling infrastructure content, and I will invite you to join the webinar on July 10th for more details.
Thank you very much, Luis. And now we will move to another presentation on transformations in the industry, in the 5 energy-intensive industrial sectors. And our next speakers are Araceli Fernandez and Kira West. And just for your information, we have this and another presentation on CCS left, and we can go a little bit over time that we've allocated for the webinar. If you could still stay with us, we could go until 4 p.m. There is time to allow some time for questions at the end. Thank you very much. And Araceli, please, and Kira.
Thank you very much. So in the next session, we wanted to go a bit in more detail on the analysis that we've done within the V2 degrees and the 2 degrees for the industrial sectors. First of all, just to put things in context, Samantha already provided what the climate ambition meant in terms of going beyond the 2 degrees. And we wanted just to put that carbon budget that was presented before in industrial terms. So basically what we could see here is that going to 2 degrees, and of course even more going to beyond 2 degrees, implies significant changes in terms of carbon emission reductions across the different industrial subsectors. We're talking about 40% and 75% by 2060 in overall direct industrial CO2 emission reductions. And as it was also discussed before, even if those reductions are very significant, that would still imply that by 2060, we still will have around 2 gigatons of CO2 emissions coming from the industrial sector. And then that means that overall, to meet the net carbon budget of being carbon neutral, by 2060, we will be required to have negative carbon emissions somewhere else in the system where this carbon reduction implementation can be more effective. So we put this into context. What we can say is that if we study industrial energy trends, we are basically not on track for a 2 degrees trajectory, not, of course, for a below 2 degrees trajectory. What we are seeing here is a historical trend of the final industrial energy consumption over time at the global level, also indicating what's the aggregated industrial energy intensity. And what we've seen is that the improvements that we've seen in the last 15 years for that aggregated industrial energy intensity indicator would need to basically accelerate quite drastically. So we'll need to triple or almost quadruple by 2030, in the next 15 years, if we were to basically get on track for this 2 degrees or below 2 degrees pathway. So what we've done in the chapter in the analysis for this year's edition is to really look at what specific challenges, current constraints, but also opportunities there are in terms of drastically reducing the carbon emissions footprint for different key materials. We focus specifically on energy-intensive sectors, mostly on petrochemicals and chemicals, crude steel, cement, also pulp and paper and aluminum, and we're just here highlighting some of those examples. The idea is that we've been looking into detail of what were the specific challenges that those some of those key sectors for societal developments were facing in terms of a drastic reduction of carbon emissions, and basically what possibilities in terms of technology innovation, in terms of different types of strategies when it comes to energy efficiency or material efficiency could be put in line to support basically the decoupling effort that is needed to basically remove the direct relationship between direct CO2 emissions and the production of those key materials. So when we look at all these different subsectors, what we end up is trying to categorize some of those strategies and changes in terms of the way we currently produce materials in 4 main categories that were a bit cross-cutting across the different industrial sectors. This is just to show you what's the relative contribution of each of these categories within the total industrial efforts for going from this reference scenario we're using in the analysis to this below 2 degrees. And basically what we've seen here is that the greatest effort is allocated to best available technology deployment and energy efficiency. That takes most of the let's say burden in terms of CO2 emission reductions. Closely followed by technology innovation, so deploying technologies or process technologies that are at demonstration states today or that are starting to be emerging in specific markets. Also, we looked at strategies related to fuel and feedstock switching in terms of lowering the carbon footprint also of different process routes, and then material efficiency as well. And that really helps not just producing materials more efficiently in the sense that reducing energy and CO2 footprint, but also had an indirect effect of lowering the demand of some of the primary materials we looked at. So having said this, then my colleague Kira West, that also was a significant let's say author and modeler also for the analysis, is going to provide some examples and further insight into some of these categories.
Thanks, Araceli. Looking at each of these levers that were mentioned in the previous slide individually, we wanted to give some examples of how they can impact industrial energy demand and CO2 emissions. So first, taking a look at energy efficiency, which as you saw was the greatest contributor of cumulative CO2 emissions reductions in the below 2 degrees scenario. Here we have 2 examples of crude steel and ammonia energy intensity and CO2 intensity. So as you can see, the reductions in energy intensity are really quite dramatic between the RTS and the B2DS, and particularly that the reductions by 2030 are quite important, and this is really the main lever that's available to be scaled up rapidly in the first half of the scenario. So the energy efficiency and deployment of best available technologies really play a very important role in bringing down energy intensity of the main industrial processes in the early years and also continuing through the end of the time horizon. Next, we wanted to look at material efficiency strategies. This can encompass quite a lot of different options. You'll see, as Araceli mentioned, there's some demand reduction if you compare the production levels in the B2DS in 2060 to the RTS, particularly in metals, and that's related to process yield improvements and scrap reuse. We also considered post-consumer recycling, so you'll see that impact in the metals production as well as in plastics. So you can see some impact on the demand for primary chemicals in the B2DS. The same applies to the pulp and paper sector. So you can see there's a greater share of recovered fiber pulp in the B2DS. And we also looked at clinker substitution as a sort of material efficiency option in the cement sector. So you can see the clinker ratio in the cement sector is reduced in the B2DS by 2060. Though this is not quite as large of a contributor to the CO2 emissions reductions as energy efficiency, it's quite an important one nonetheless, and something that needs to be considered in terms of its energy and CO2 impacts. Next, we have an example of high-value chemicals production to illustrate the impacts both of fuel and feedstock switching, but also of switching process routes within the production of a particular product. As you can see in this particular example, in the B2DS, as time goes on, the production of high-value chemicals shifts away from traditional steam cracking processes, and the naphtha catalytic cracking process takes on more of the total production. You can also see the shift in fuels and an increase in the bioethanol to ethylene process, so some impact in switching feedstocks as well. So here the importance of considering these different processes and fuels as a whole, and what the total energy and emissions impacts can be is quite important as well throughout the entire time horizon of the scenario. And finally, we wanted to look at CCS and innovative processes as the final quite important lever in the B2DS. As you can see already in the 2-degree scenario in green, we have quite high rates of CO2 captured and stored in some of the main industrial sectors, the main energy intensive sectors in chemicals, cement, and steel. And to reach the B2DS, you have to really be even much more aggressive than what's already seen in the 2 degrees. So the blue dots in some of the processes reach nearly 80% of CO2 emissions captured and stored. So this is quite aggressive compared to where we are today, and we'll have a bit more of a look at CCS later in the webinar. And finally, we wanted to just point out that we've given some global examples here, but that regional differences are really quite important, particularly in the industrial sector. Here you can see the production of hot metal in the iron and steel sector by region. And while you see from 2014 to 2060 in the RTS and to a greater extent in the B2DS, there's a shift away from blast furnaces, but the mix of EAF based on scrap or based on DRI and smelt reduction differs quite a lot by region. And this is quite dependent on the availability of materials in each of these regions, the availability of scrap, the existing capacity structure, as well as the policy context and the relative energy prices. So just to wrap up, we have some industry-specific policy recommendations. First, standards and incentives are quite important no matter what scenario is put in place. mitigating the risk of developing innovative energy technology, also quite important, particularly as the scenarios become more ambitious. Public-private and cross-sectorial cooperation is a key to also enabling that innovation that plays such an important role in our scenarios. As I mentioned, material efficiency is something that should be considered not only in terms of its potential for reducing material use, but also as a part of any energy and climate policy. And similarly, heat mapping is something that can identify cost-effective opportunities for reducing the energy and CO2 impact of the industrial sector. And in order to better form policy in all of these areas, improving the availability of data and energy performance statistics in the industrial sector is something that we see as really an important key. And then finally, just to emphasize, the B2DS, as we saw, is really extremely ambitious and will require an even more rapid scale-up of the technology options that we saw in the 2 degrees, which is already an ambitious scenario. And I think with that, I will pass it on to the next presenter.
Thank you very much, Kira. And now we'll move to the final presentation in this webinar. As you probably noticed already, we talk a lot about carbon capture and storage. It was very much present in the presentation by Uwe about the electricity sector decarbonization. It was also very much there in the presentation on decarbonizing the industrial sectors. So now we will have a detailed examination of the role of CCS, especially in the 2DS and B2DS scenarios, and how CO2 transport and storage infrastructure development can help unlock the potential of CCS. And I give the floor to Tristan Stanley, the energy analyst in the carbon capture and storage unit at the IEA. Tristan, please.
Thank you, Alina, and hi to everyone out there. We're going to have a look today at the role of CCS across both the 2DS and the B2DS scenarios. But as we heard earlier, firstly I'd like to highlight that CCS really isn't on track to meet the levels of deployment and penetration set forth in either scenario. We'll touch on that a little bit later, but I think it's important to open with that as a context. In particular today I want to focus on the role of CCS in the B2DS and how the application of CCS differs between the 2 scenarios. As you'll see, CCS is applied extensively across the power, industrial, and also the fuel transformation sectors. And again, to highlight that if we look at where we sit at the moment, you can see it doesn't actually even show up, highlighting again the dramatic increase in efforts that are needed. If we look at the 2DS this year and compare it to the 2DS last year, in last year's ETP, one of the things we notice is a much slower deployment early on in the period. This is essentially due to a lack of projects currently entering the pipeline. As a result, and given the long lead times of particularly developing CO2 storage, the level of CCS out to 2030 is significantly lower than the ETP 2016. However, by the time we reach 2050, the level of CO2 captured annually has essentially caught up with the rate in the 2DS in 2016, highlighting that despite the slow deployment to date, CCS continues to play a key role. So looking at the key changes in CCS between the 2DS and the B2DS, firstly there's more. There's a lot more CO2 being captured and therefore a lot more CO2 needing transport and storage. We see a wider deployment of CCS. As CCS sees greater penetration across the power and industrial sectors, the locations and facilities needing to apply CCS and CO2 capture will increasingly be more geographically spread. Accessing more isolated facilities presents a significant challenge for particularly transport and storage infrastructure. And we also have smaller sources of CO2. CO2 is captured from smaller and more diluted sources as the emissions constraints become more and more emissions available decrease more and more. At present, this causes a significant cost penalty, and so we need innovation to improve the performance of capture technologies, particularly as they apply to small and diluted sources. Looking at CCS in the power sector, we see here the application of CCS on capacity across the coal, gas and biomass fuel sources. You'll see the darker portion of the bars is the share of the capacity with CCS applied. You'll note that in coal, by 2060, CCS is essentially applied to all coal generation capacity. When we look at the gas sector, however, and the biomass sector, CCS is still only applied to around 20% of capacity. Despite this, most of the generation hours, particularly in coal and gas, come from the plants with CCS. This highlights that in 2060, in a B2DS world, plants still fossil fuel plants which are unabated have very few operating hours, as plants with CCS are increasingly preferred. There is extensive retrofitting of CCS, particularly to coal. As Uwe mentioned earlier, around 170 gigawatts of coal capacity is retrofitted over the course of the B2DS. But despite the availability of retrofitting, we still see significant retirements of both coal and gas, but in particular coal in both the 2DS but also in the B2DS. As Uwe mentioned, there's around 1,300 gigawatts of capacity that is still retired, of coal capacity which is retired early, despite the availability of CCS retrofits. This again highlights that CCS will play a key role in the power sector. However, it won't completely remove or avoid stranding existing assets. As we move towards 2060 in a B2DS world, again, as Uwe touched on, coal and gas generation, even with CCS, becomes a high emissions generation source. As a result, and you can see in the bottom blue line, the generation hours from coal in particular decline, with coal with CCS decline from 2045 as you approach 2060. If we're able to increase the capture rate, that is the proportion of CO2 which is captured from the essentially from the flue gas, up to 92 or 95%, it significantly changes the role that CCS plays in the power mix as we approach 2060. At a 95% capture rate, you see that CCS, rather than declining, stays constant at around 2,750 terawatt hours. Again, this highlights key areas for innovation and research and development to reduce the costs of capturing higher proportions of CO2. With present technologies, going to these rates significantly increases the efficiency penalties and therefore the cost of applying CCS. Moving to the industrial sector, and we've heard about the role of CCS in the industrial sector previously, so I'll just touch on a few points here. One of the big things we see is that the increase in CCS between the 2DS and the B2DS is much greater in the industrial sector than it is in either the power or the fuel transformation sector. CCS plays a particularly large role in the cement, iron, steel and chemical subsectors. One of the increase in the application of CCS sees a much higher penetration of CCS in the production of key materials. By 2060, the share of steel production with CCS applied at some point in the production process increases from around 20% to almost 60% in the B2DS. From the 20% in the 2DS to around 60% in the B2DS. In the cement and chemical sector, by 2060, CCS is applied to 90 to 95% of production, up from 40 and 30% respectively in the 2DS. The greater penetration of CCS again presents some significant challenges, particularly when we look at CCS from an infrastructure perspective, and I'll go into that a little bit more later. But it's likely that early CCS projects will be located along CO2 transport corridors, or at least within easy access of CO2 storage or transport. As the penetration of CCS increases, we'll need to access those more isolated facilities as they begin capturing CO2. This, of course, greatly increases the cost of the transport of CO2 and the transport network. And similarly, in the transition to such high penetration rates, policy and regulation will need to account for facilities that don't have as easy access to CO2 transport and storage. Moving on, I'll touch briefly, and this is again being covered earlier, on the role of BECCS in the B2DS in particular. As Samantha mentioned in the opening, the use of biomass between the 2DS and the B2DS is largely constant. However, we do see a significant increase in the amount of bioenergy with CCS applied to it. We see that the total amount of CO2 captured from biomass and bioenergy fueled facilities rises from around 2.7 gigatons in the 2DS in 2060 to almost 5,000 gigatons in 2060 in the B2DS. And as has been discussed, this is particularly critical in generating negative emissions to offset the remaining emissions in other sectors. And again, to highlight that it's the use of BECCS in these various applications that allows the power sector to reach net zero emissions. And finally, if we look at where CO2 is captured from in looking between the 2DS and the B2DS, again we see that, and I've highlighted in particular the low concentration and small sources. We see that CO2 needs to be captured from much more difficult places. Now, the implications of this, as I mentioned earlier, are that we need to find technologies or innovate and develop the current technologies to such an extent that they can capture from these either smaller sources or these sources with a lower concentration at a more affordable rate and without the significant efficiency and energy penalties that they currently come with. And you'll also see here that the overall, that again, through the combination of CCS and biomass in the B2DS, we end up with net negative emissions in the low concentration, large and the high concentration sources. So how do we get to these levels of CCS? We focused this year on transport and storage and its role in unlocking the potential of CO2 capture and CCS in particular. If we look at the scale of the transport and storage requirements, we see that single end-to-end projects won't get us there. It's critical that we develop transport and storage infrastructure with common user infrastructure. And it's clear that at the moment and for the foreseeable future, it's of a greater public value than is realised commercially at the moment. So public sector leadership will be critical given the lack of commercial drivers, and also to overcome the chicken and egg or the sequencing problem in which investment in capture is unlikely to go forward without transport and storage options being available, and similarly investment in transport and storage is unlikely to go ahead if there is no source of CO2. again, the public sector will be critical in breaking this deadlock. Understanding the problem as an infrastructure problem is one of the first steps. So similarly, our policy recommendations or the areas of focus in terms of policy coming out of this year's ETP for CCS focus on the development of storage and transport infrastructure. Developing storage sites and storage resources should be a key priority, beginning with resources located near clusters of emission points. Governments should also consider mechanisms which insulate the CO2 capture from CO2 transport and storage to ameliorate the counterparty risk which has hampered many projects to date. We also see that if transport and storage are available and are sufficiently de-risked, it opens up a range of other policy options for governments in which a combination of regulation and support can drive the uptake of CO2 capture across the economy. So in conclusion, again, I would just highlight that the role of CCS in both the 2DS and the B2DS is quite significant and is significantly higher than what is suggested by the trajectory we're currently on. And we, coming out of this analysis, see the key to unlocking this level of deployment as being investment in transport and storage, in particular from the public sector. And in doing so, leveraging significant private investment in CCS. I'll leave it there and pass back to you, Alina.
Thank you very much, Tristan. And we're at the end of the presentation session, and thank you very much to all the speakers for trying to fit very comprehensive analysis and 40 pages chapters into 10, 15-minute presentations. I hope you have, the audience has a lot of food for thought, a lot of new information. We several questions, and I'll probably start with the questions on industrial presentation. There was a question whether final energy consumption in industry includes feedstock. I'll probably list all three questions and let Araceli and Kira respond. Another question was about carbon capture and storage, whether CO2 is captured just from the combustion or also industrial processes in industry. And the third question is what type of technologies have we considered in analysis in terms of innovation? So Araceli and Kira, please take those three questions.
Okay, thanks, Alina. So the first question about petrochemical feedstocks. So in the slides that we've shown today, when we were referring to final industrial energy use, indeed, energy use as petrochemical feedstock was included. So there was a slide also showing energy intensities, energy consumption for high-value chemicals, for instance, and that one will also include energy use as feedstocks, mainly naphtha and ethane. So that's why you will see quite big shares of oil consumption within that. Then there was another clarification question about CCS and whether within carbon capture emissions in industry we're considering energy-related and process-related emissions. So indeed that's the case as well. Within the industry models, we model separately streams for energy-related emissions and process emissions when they are generated separately in the process, or when they are combined, they are also combined in the model. But in any case, there's a difference in terms of carbon capture technologies and related energy requirements because of the different characteristics of those two streams. In some cases, some of the process CO2 streams can be more concentrated in terms of CO2 than energy-related emissions. That's not always the case. There are some exceptions, but that's quite a typical trend. And in that case, then the carbon capture technologies applied normally tend to achieve high capture rates with lower energy requirements, and they are more electricity-based. So those type of considerations are included. And then there was a more generic question about what type of technologies or strategies we consider within the category that we were referring to as innovation. So as an example, well, I mean, carbon capture technologies, CCS in general was included into that category. But normally, when we refer to innovative process technologies, we are referring to process technologies that are demonstration stage today, that we think that within the time horizon of the modeling exercise could be coming into the market, but that they are not either commercially available today, or they are at very early stages of market development. These are the ones that are, let's say, quantified within the scenarios, and that would range from different types of process technologies upgrades that would enhance the integration of carbon capture, that could also include completely different routes using, for instance, or shifting from fossil-based fuels or feedstocks, to biomass-based feedstocks. And for instance, there's a few examples on the chemical sector, but that would also include, for instance, completely different technologies, process technologies that are using hydrogen, and especially renewable-based hydrogen as a feedstock for, let's say, that process. The other point I wanted to make on this is that there's other types of options from the technology perspective, more at earlier stages of development within the innovation cycle. And for those ones, I mean, we've kind of quite comprehensively, let's say, consider or discuss them throughout the chapter. But in terms of quantifications within the scenarios, those ones are demonstration states, at least that are the ones included, because are the ones for which we manage basically to get techno-economic information that could be robust enough so that the list cost comparison could be done. But certainly, I mean, there's also discussions about earlier stages of technologies in terms of development, or more breakthroughs that are also in the pipeline and could have a significant role in the future if their development is accelerated in the coming years.
Thank you very much, Araceli. There were a couple of questions on related to the electricity sector. One question was on remote locations in developing countries, and especially in Africa, and which technologies we considered in the model to deliver electricity to millions of people in distributed locations. A related question was on the level of renewable penetration in 2060 in the model. So maybe I let Luis and Uwe respond to these two questions.
Thanks, Alina. So on the first question, which was on what types of technologies can reach remote areas, particularly sub-Saharan Africa, I would say the first technology may be a bit unusual, but it's more related to mapping of where electricity networks are, and related to better planning of networks. So in many cases, what we see is that there's a lot of populations that are not actually that remote, but very often either the local transmission network operator or distribution network operator or the government, they don't actually know where the electricity networks actually extend to. And there's a lot of populations also that are not even off-grid, that are what we call under the grid. So they're close enough to receive access to electricity, but there's a host of issues that are not so much related to technology, sometimes they are, but that do not allow them to actually gain access to electricity, to energy. So that's one aspect. Then the second aspect, I think, is better planning, like more transparency as to where the electricity network will be built, what the plans are from governments and network owners and operators. This is a huge barrier for some of the technologies that I imagine the question is more aiming at, which is more of the distributed solutions, where there's a lot of uncertainty as to whether there is a business model or not, because once the grid arrives, then it becomes competing or even a stranded asset. And in terms of what I think the question is more aiming at, which is whether kind of distributed technology options, there's, as we have highlighted also earlier in the presentation, very significant cost reductions from the generation side, from solar PV, which is the main growing market right now for remote energy access, remote electricity access. Also cost reductions for batteries. In some of these cases, it's not actually lithium-ion batteries, it's lead-acid batteries, but a growing number of lithium-ion battery solutions. And then there's also reducing costs and more kind of innovation happening on the integration of these packages, sides, let's say, where mini grids are being built at a lower cost, and they're being packaged with business solutions also related to digitalization, to mobile payments and so on, that are making it very interesting. So one very interesting aspect is when a lot of solutions in Africa, they're now getting enough data from the bottom up, from these remote plants that are being installed, that they're really able to optimize much better how these things should be installed, the maintenance schedules. They're really able to save a lot of operation maintenance, which is a problem when you're doing millions or thousands of small systems rather than doing a centralized grid. So yeah, I would say that's kind of the suite of technologies: distributed solar PV, smart home systems, and so on. The other aspect, maybe final aspect I'll highlight on that, is that some of these solutions for remote access, there's a question as to how scalable they are, because in many cases there are lifeline solutions where one provides mobile phone charging, maybe some LEDs, a battery for a couple of hours of lighting in the night. But these systems are not easily scalable once the demand grows, once there's businesses that demand more energy services and so on. So what we are seeing now is that mini grids that are being built with certain specifications, they're being built with trying to obviously reduce costs, but then they're not ready for connection with the network. So then the network grows, these countries develop, one day they need to connect, and these networks become a stranded asset. So that's also a very important consideration. And so finally, I will just direct the audience to plug the IEA's Energy and Development Special from the World Energy Outlook, that we look in a lot of detail into many of these issues coming in the fall.
Yeah, coming to the question.
Please take into account we have 8 minutes time and still questions coming in.
Yeah, just a brief note. I mean, I talked already a bit about renewable penetration or the share in my presentation. So in both scenarios, the 2 degree, but also the below 2 degree, we see a share of around 3/4 of electricity globally, on the global average, being generated from renewable sources. Particular dominant renewable sources, I mean, also a bit following the current cost trends that we see for some of renewable technologies. We see solar PV accounting for 70% of the global generation mix in 2060 in the below 2 degree. We have a combined share of onshore and offshore wind of almost 20%, again in 2060. And also, if we should not forget about let's say, the more traditional renewable sources, particularly if we look at hydro, which also is today the largest low-carbon electricity generation source, which accounts in 2060 also 70% of the electricity generation. And one should also consider, particularly if we talk about hydro, that it also can provide what also Louis discussed, flexibility to the electricity system. So that's also true if we talk about bioenergy or particular biogas. That was an option to provide flexibility, so switching from natural gas to biogas as a fuel for gas-fired power plants. Then we can also talk about the more system-friendly deployment of renewables. So we talk there about wind, which has a more steady profile, so called low wind speed turbines, or also considering solar PV panels, which have maybe different orientation, that not necessarily optimized to maximize the power output, but have a more steady profile. So there are options to then also ensure that the increasing share of renewables, also part of this renewables, actually also providing some flexibility or less impacts or less needs for flexibility from other sources in the electricity system.
Thank you very much, Uwe. There are many questions coming on CCS, and I invite everybody who would like to know a bit more about CCS, send us an email, because we won't be able to respond to all the questions. Maybe I'll just ask a general question and let Tristan to respond in 2 minutes. Why we have CCS in the model? Why do we need it? Cannot we decarbonize just with renewables and improved efficiency?
Thanks, Elena. I'll just make 1 or 2 comments very quickly, and then either Uwe or Araceli may want to add to them as they pertain to their particular sectors. In short, CCS does play quite a dominant, well, not a dominant, but a significant role in the modelling. In the power sector, can we do without it? Well, possibly. At what extra cost? I'm not sure. Uwe perhaps could comment on what the implications of that may be. My understanding is that in the industrial sector, it's quite a lot harder to meet the targets in the 2DS and B2DS without CCS being available. I suppose there's also a more philosophical question here, and that is, should we be ruling out any technologies given the extent of the challenge that we're facing? So even looking at the 2DS, the changes that we're talking about in the energy sector are very, very significant. So to rule out a potential contributing technology is perhaps doesn't necessarily help us achieve the significant emissions goals we're trying to get to. When we're looking at the B2DS, I think the challenge becomes much, much greater. Again, as we've highlighted here, the B2DS is essentially us pushing the technologies we have as far as we can, and so to remove one of those technologies puts significantly more pressure on the remaining technologies and is likely to drive up the cost.
Well,
sorry, just to add to that also, the beyond 2 degree scenario relies significantly on negative emissions in reaching net zero emissions by 2060. Now, at the moment, the only technology we have for this is combining CCS with bioenergy. There are others on the horizon, but this is the only one that we consider to be sort of in the development pipeline. So I think in that sense, it also is quite critical for offsetting the remaining emissions elsewhere.
yeah, thank you very much, Tristan. I think we'll need to stop here because we have only 3 minutes left in this webinar that it's already a bit over time, ran over time. Just to leave you with maybe 3 concluding remarks. As you could see in the presentations that provided only half of the book, that a portfolio approach is absolutely necessary in order to decarbonize energy sector. So all technologies are needed, and one cannot replace the other and play a bigger role if something is not available. Another message is that policy will be driving the technology deployment. So there is a huge need for policy intervention in order for these technologies to play their role and meet the potential that is assigned to them. And maybe the third question is that innovation is critical in the energy sector, and we see a lot of innovation already, but as you could see in the slide presented by Kamal and Samantha, the investments are still below what is needed, and the investment in new technologies and technology innovation is absolutely necessary in order to decarbonize and modernize the energy sector. So I would like to thank all the participants and the speakers, and also would like to invite you to come to the webinar on July 10th, where we'll present again the global outlook and buildings and transport sector decarbonization strategies, as well as bioenergy, because there were many questions on biofuels and bioenergy, and I hope all of them could be answered on July 10th during the presentation at that webinar. And also, for you to know that the webinar was recorded, so you will be able to listen to it maybe next week already, and we'll put the presentations on our webpage. And we have executive summaries in 7 languages on our webpage that you can have for free. And the ETP publication could be bought on our online shop, either in hard copy or electronic version that has also access to all the spreadsheets and graphs and all the data that were used in order to produce this report. Well, thank you very much again, and we look forward to seeing you again. Goodbye.